we're going to be looking at two things. Number one, how do we figure out where a function is increasing or decreasing? Okay, using the derivative of the function, that's number one. And secondly, how do we figure out if the function is at a maximum or a minimum point? Okay? All right, so firstly, where is a function increasing or decreasing? Well, when a function is increasing, okay, the slope of the tangent line when it's increasing is positive. Okay, so if a function is increasing, okay, f prime of x is going to be positive. When the function's decreasing, the derivative is negative because the slope of the tangent line would be negative. Okay? So for example, if we look at something like this.
Caretaking, please call 2311. Caretaking 2311, please.
Okay? The function is increasing essentially up to this point. Okay, so it's increasing, and then it starts to decrease. Okay? If you look at the slope of the tangent line up to the max point, the slope of the tangent line is positive up to that point. Because if we were to draw a tangent anywhere up to here, that tangent would slope upwards to the right. Once we get up here at the max point, the tangent line would be horizontal, so the slope would be 0. And then once we go sort of over the hill, we're going downwards to the right, and so now the slope would be negative and the function's decreasing. Okay, does that make sense? So here this is like positive, 0, negative. Okay, now what we're looking for to figure out where that happens, where is the function possibly going to change from increasing to decreasing or decreasing to increasing, is we're looking for some points on f of x and some x values, and those x values are called critical values or critical numbers. Okay, so what we want to look for, okay, so where am I going to write this? Maybe I'll write it over here. To tell where a function might change, doesn't always, but it might, from increasing to decreasing or decreasing to increasing, look for critical numbers. For f prime of x. Okay, and I'm going to tell you what those are in a minute. Critical numbers are any x value where the derivative of the function is either 0 or undefined. So these occur when f prime of x equals 0 or f prime of x is undefined. Okay? And something happens at those points, so we want to be aware of those. All right, so let's see how this might work. Okay, so for example, find the intervals where f of x equals 3 plus 7x minus 3x squared is increasing and decreasing. Okay, so find the intervals where f of x equals 3 plus 7x minus 3x squared is increasing and decreasing. So to do this, we need to find the critical numbers or critical values for f prime of x, which means we've got to find the derivative. Okay? When the derivative is either 0 or undefined, because if you look up here, right, this function happens to actually be quadratic. You can see when the derivative is 0 in a quadratic function, that is the point where the function actually switches from either increasing to decreasing if it's a max point, or if it's a min point, it's going to switch from decreasing to increasing. Okay, so you can see in a quadratic function how that critical value in the derivative, the point where the slope of the tangent line is horizontal, is actually going to tell us that the function is going to switch from increasing to decreasing or vice versa in this case. Maybe not in other cases, but in this case it will. Okay, so we've got to be conscious of that. Okay, so what we're going to do is we are going to find the derivative. Okay, so f prime of x in this case is going to be 7x minus, or sorry, my bad, 7 minus 6x. Okay. Now, the critical numbers, in this case, f prime of x is continuous everywhere. It's not discontinuous anywhere. It's a linear function. So the critical number is going to occur when f prime of x equals 0. Okay? Okay, and in fact, because this is linear, we can actually solve it directly within the inequality. So I'll show you how to do that both ways. We can solve this one directly, but that won't be the case for the rest of them. Okay, so if we solve this, we're going to get 6x equals 7, which means x equals 7 over 6. Okay, so essentially, if this is sort of our number line, here's 7 over 6. Okay, what we want to know is what happens on either side of that to f prime of x in terms of its sign. Okay, so let's say we look at the value, we take any test point. Let's say x is 0. If x is 0, for example, f prime of x would be 7, which is what? Positive or negative? Positive. So everything here is positive. Okay? Let's say we take something greater than 7 over 6, maybe 2. Okay, 7 minus 6 times 2 is 7 minus 12 is negative 5. That's negative. Okay, here f prime of x is 0. So anything to the left of 7 over 6, when x is less than 7 over 6, the function is increasing because the derivative is positive. Anything to the right of 7 over 6, when x is greater than 7 over 6, the function's decreasing because the derivative's negative. Okay? So increasing when x is less than 7 over 6. And this will decrease when x is greater than 7 over 6. Okay? And essentially, the parabola has an axis of symmetry at 7 over 6, right? The x-coordinate of the vertex would be at 7 over 6. Okay? And at 7 over 6, that's going to be a max point. The derivative is 0, so it's not going to increase or decrease at that point. Okay, now this one you could solve without the number line because the derivative is linear. So if you wanted to, you could also go like this. Where can I write? Maybe I'll write this up here because I'm running out of space. You could also just go directly into this. If f prime of x equals 7x, or 7 minus 6x, you could say it's increasing when this is greater than 0 and solve that inequality, right? So you would have something like 7 greater than 6x, right? Which means divide by 6, 7 over 6 greater than x. Okay, and it's going to decrease when the opposite inequality goes in there, when the derivative 7 minus 6x is less than 0. Right, so we're going to have 7 is less than 6x, which means 7 over 6 is less than x. Okay, which is the same thing that we got over here. Okay, and because this is linear, we can solve this directly by putting the inequalities directly in. Okay, but that's not going to be the case when our derivative is not linear, and we're going to do some of those right now. Okay, any questions so far? So far, so good? All right, so where is this function, f of x equals x times 2 minus x all cubed, increasing or decreasing? Okay, so again, first step here is we've got to look at the derivative of this function and then set that equal to 0 so that we can see the critical numbers, the critical values. Okay, so that's where we're going to start. Now, this is a product rule, and here we're also going to have to do the chain rule. Okay, so f prime of x is going to be x is u, 2 minus x all cubed is v. So u prime v, derivative of x is 1, times 2 minus x cubed, that's v, so 2 minus x cubed, plus uv prime, so x is u, and the derivative of 2 minus x cubed, this is a chain rule, so we're going to have 3 times 2 minus x squared times the derivative of this part, which is negative 1. Okay, and I'm just going to simplify this a little bit. So this is still just 2 minus x cubed. And here we're going to have negative 1 times 3 times x. So minus 3x times 2 minus x squared. And we essentially want to set f prime of x equal to 0 and solve for x. So some of you guys were asking me earlier last week, well, would we have to factor this? we have to factor this derivative and factor out those common binomial factors. This is where the factoring the common binomial factors is really important, right? If you wanted to set this equal to 0, currently this isn't actually factored because we don't have a bunch of things multiplied together to equal 0. If we had a bunch of things multiplied together to equal 0, we could solve for x quite easily. But we don't have that right now. Okay? And so we need to get there so that we can achieve our goal of figuring out when this derivative equals 0. Okay? So we're going to take out, we have 3 factors of 2 minus x here and 2 factors of 2 minus x here. So we can take out 2 of them. So I'm going to take out a 2 minus x squared, and here I'm going to be left with 1 factor of 2 minus x. And here I'm going to be left with minus 3x. Okay, and then I can simplify this second bracket over here. And that gives me 2 minus x squared times 2 minus x minus 3x is 2 minus 4x. And then this has a GCF of 2, so I'll take that out. And all together, I'm going to have 2 times 2 minus x squared times 1 minus 2x. Okay, and that is my derivative factored. And when it's in this form, if I set it equal to 0, I can very easily see the values of x that'll satisfy that equation. Okay, so that's what I'm going to do. Okay, and from this factor, or there's 2 of them, but it's the same factor twice, the 2 minus x squared, I get x equals to 2. And from this factor of 1 minus 2x, I get that x equals 1/2. So those are my 2 critical numbers. Okay? Okay, so I'm obviously going to have to do this question on another page because I'm totally out of room. So we'll do that. I'm just going to continue down here, and then I'll bring up another page to do this one. Okay, so now we could take test points on a number line. You can totally do that like we did with the last one, but there's a lot of stuff to plug in here. So there's another strategy that we could use. Essentially, these 2 critical numbers divide the number line into 3 sections, okay? So the 3 sections are here. One section is from a half to negative infinity. The other section is from a half to 2. And the third section is from 2 to infinity. And we need to know what's happening with the sign of the derivative in those sections, okay? Because these are the points where the derivative is 0. So between those points, the sign isn't going to change. It's going to be the same. Right? So it's not like between a half and 2, it's going to go from positive to negative. It will only change signs from, like, between intervals. Right? So it could change as it goes from one side of a half to the other side, or from one side of 2 to the other side of 2. But it's not going to happen anywhere else on the number line. Okay, so we've got to know what's happening with the sign of f prime of x, because the sign of f prime of x tells us where the function is increasing or decreasing. Okay, so we could just take test points and put in a value of x. You can absolutely do that, right? So you could say, okay, well, I'm going to test x equals 0, I'm going to test x equals 1, I'm going to test x equals 10. And that totally works. But what you might find is, especially as we get derivatives that get a little bit tedious, and we've seen those, that can be kind of lengthy and annoying. Okay, so there's another thing that you can do, which is this. We can look at intervals. I'm going to make a little chart. So the intervals that we're looking at are negative infinity to a half, a half to 2, and 2 to infinity. Those are sort of the three sections of the number line that we're examining. And then what we can do is we can look at the factors that we're multiplying together in f prime of x. So I'm going to just rewrite f prime of x, just as a reminder, was 2 times 2 minus x squared times 1 minus 2x. Okay, so there's that, and that, three pieces. So I'm going to write those factors down. There's 2. There's this piece, 2 minus x squared. And there's 1 minus 2x. Okay, and then I'm also going to have a column for f prime of x. And what we're going to do is we're going to record the sign of what each of these factors would be in each of these intervals. Okay, so 2, it doesn't depend on x. So 2 is positive everywhere. So these are all positive. Okay. 2 minus x does depend on x, but we square it. So if it's negative, once we square it, what's going to happen? It's going to be positive. That's right. Okay? So all of these are also positive. It doesn't matter where we are. Okay? This is the one that might change. Okay? So let's take a look at that. If we're in this interval, right, let's say, what number's in this interval? 0. That's a nice easy number to put in here. This would be 1 minus 2 times 0, which is positive. Does that make sense? So this is positive. Okay? In this interval, a nice easy number to test would be 1. Okay, so we could test 1. This would be 1 minus 2 times 1. What sign is that? Negative. Okay, in this interval, we could test, I don't know, anything, 3, 4, 5, 10, 100, doesn't matter. Okay, so let's test 3. 1 minus 2 times 3, positive or negative? Negative. Okay, now to get f prime of x, we multiply these together. Okay, so in this interval, f prime of x is positive times positive times positive. What's its sign going to be? Right. In this interval, it's positive times negative. Right. In this interval, it's positive times negative, so it's negative. Okay, so for this function, okay, the function is increasing in this interval and decreasing in these two intervals. Now, because this function is continuous. Because the critical numbers were not points of discontinuity, we can join these two together. Okay, so where does the function increase? It's going to increase here. It's going to decrease from 1/2 all the way to infinity. Okay, and these can be joined since it's continuous. Okay, if it's a point of discontinuity, if that's the type of critical number, then you can't join them. You'd have to write it as two separate intervals, because it would decrease and then there'd be a little stop and then it would decrease again. Yeah.
So do we have to do this every month here?
Well, the other option is that you could take a test value, and for this one it wouldn't be terrible, right? You could take just a test point in here, and in here, and plug that test number into this derivative. Okay? Yeah. Yeah. Okay, so the question was, do you have to join them together? Well, this is kind of what the function looks like. So if you look at the original function, do you see how this factor is 2 minus x cubed? That is a triple zero. Okay, so if you look at, it's easier to kind of see what's happening there, to think of y equals x cubed, because it's the same sort of thing that's happening. Okay, it's the same type of zero as y equals x cubed. If you look at y equals x cubed, okay, this is increasing everywhere. So if you didn't join them, you'd be saying it's not increasing there. Okay, so what you could do, I suppose, is you could say that. Do you guys know what this symbol means? No? Union? Yeah, okay, so this union, this symbol is when you join things together. Okay, it comes from set theory. Okay, it means we're joining these two sets together. But we have to kind of include that value of 2. Okay, now if you made that mistake, it wouldn't be huge. It would be a very tiny, teeny little spot of an error. So I wouldn't worry too much about it. And the reality is that I shouldn't say most of the time, but often when the derivative is 0, okay, the function does most of the time switch from increasing to decreasing, but not always, right? Often it's a max-min point, right? When it goes, it sort of goes increasing, horizontal, and then decreasing. Okay, but you can have like a triple zero like this, where if you look at it on this side, this looks like it's approaching a max point. So there's approaching a horizontal asymptote here, and on this side, it's approaching like a min point. Okay, we're going to learn about these when we look at the second derivative test. This is called a point of inflection. Okay, so there's more to come on that. But most of the time, this doesn't actually happen. Most of the time, it'll switch signs when the first derivative is 0. Okay? All right, let's do another example, and we're going to do this one. So f of x equals x over x squared minus 1. Okay, let me pull up a new page. Okay, so if we're going to find the derivative of this, this is a quotient rule plus a chain, no, not a chain rule, never mind, sorry. It's just a quotient rule. So u is x, u prime is 1, v is x squared minus 1, v prime is 2x. Okay, so if we're looking at f prime of x, it's u prime v, so that's 1 times x squared minus 1 minus u v prime minus x times 2x over v squared, which is x squared minus 1 squared. Okay, and if we sort of clean this up a little bit, this is going to become x squared minus 1 minus 2x squared. So that is negative x squared minus 1 over x squared minus 1 squared. Okay. Now, critical values. When your derivative is in the form of a rational expression, which this one is, the critical values happen when either the numerator is 0, because when the numerator is 0, the derivative is 0, or when the denominator is 0, because when the denominator is 0, then the derivative is undefined. Okay? So, if the numerator f prime of x equals 0. Okay, so if we try and look at that, negative x squared minus 1 equals 0, we try and solve that, we're going to get negative x squared equals 1. Or x squared equals negative 1. When does that happen? Right, not very often. Good answer, I like that. Right, this never happens. So we don't get any critical numbers from the numerator because the numerator is never 0. Okay, so this derivative will never be 0. Okay, this happens never. So no critical numbers from the numerator. Okay, but we do get critical numbers from the denominator because this could be 0. Right, so if the denominator equals 0, then f prime of x is undefined. Okay, so that would be the type of critical number that we would have. And either one of these can make the function switch from increasing to decreasing or vice versa. Okay, so let's take a look at that. We're going to have x squared minus 1 squared equals 0. Well, that would have to mean that x squared minus 1 would have to equal 0, right? Because if you take the square root of both, you're going to get x squared minus 1 equals 0. Okay, what would x have to be? 1 or negative 1, yeah. So x equals plus or minus 1 are the critical numbers. Okay, so we've got negative 1 and 1. Okay, and we can do the same sort of thing that we did in the last example where we have a chart. Okay, again, we have 3 intervals here. One of them is from negative infinity to 1. Or sorry, negative 1, my bad. One of them is from negative 1 to 1. And the third one is from 1 to infinity. Okay, and what we need to look at, f prime of x is basically a numerator divided by a denominator. So we have to look at, in each of these intervals, what would the value of the numerator be, and what would the value of the denominator be? Okay, so the numerator is negative x squared minus 1. The denominator is x squared minus 1 squared. And the derivative is the one divided by the other. Okay. So the numerator, it's negative a square minus 1. What's the sign of that going to be? Negative. Does it matter what x is? No, it's negative everywhere. Because x could be positive or negative. Once you square it, it's positive, right? If you take the negative of that, then it's negative, and you subtract 1. It's still negative. So these are all negative. Doesn't matter what interval you're on. Okay, here we're looking at x squared minus 1, and then we square that. What's the sign of that going to be? Positive, yeah, because it doesn't matter what's inside here. It's going to be 0, right? Because we're not including the points, firstly, f prime of x is never 0. We've established that. Okay, and it's not undefined because we're excluding the values, negative 1 and 1, where that could happen. Okay, so this is positive everywhere because it's a square. Okay, f prime of x is numerator divided by denominator, negative divided by positive. What's the sign of f prime of x? Negative, negative, negative. Now, what does that mean about where it's decreasing? Well, we can't say everywhere. We can't say it's decreasing on x as an element of the reals because there are 2 points of discontinuity. There are 2 points in the original function where the function is undefined, right? When x equals 1 and negative 1. So this function is decreasing Well, there's 2 ways that you can write this. You can say it's decreasing here, negative infinity to 1, negative 1 rather, that's the second time I've done that, unioned with negative 1 to 1, unioned with 1 to infinity. These symbols come from set theory, and they basically mean you're joining those sets together. Okay? Or you could say it's decreasing for x is an element of the reals, but x cannot equal negative 1 or 1. You could do it that way as well. Okay, but what you'll find is that the more and more math you do, the more we use interval notation versus this sort of notation. Okay? All right. Questions so far? We're good? All right. Now we're going to talk about max and min points. Okay, so max and min points. Okay, so let's just draw a little graph. Okay, so I'm just going to draw, let's say we have a graph with endpoints. Actually, no, I'm going to make this one a little higher. There we go. That's better. Okay. So you guys have seen something like this before, I assume? Yes? Okay, cool. So have you guys heard that there are two types of max and min points to a function? An absolute max or a local max, or an absolute min or a local min? Have you heard of those words before? Okay, cool. Let's talk about that. Okay, so any of these, I'm going to just maybe draw them in red. Any of these points can be called max or min points. Okay? An absolute max point is the maximum value of the function everywhere over the entire domain of the function. So you're looking in this interval, where is the absolute highest point on the function? It's this endpoint. Okay? This is the absolute max. So highest or lowest values everywhere. That the function's defined. Okay? The absolute min, where would that be? Yep. Yeah, the first min, because I know I should have maybe made it more obvious, but this is the lowest one. Okay, so this is the absolute min. Okay. All of the rest of these points are called local maxes or local mins. And essentially they're called local max or local mins because locally, close by, they're the max point to the points close to them. Or they're the min point around the points close to them. Okay, so a local max or min is max min value to the points close by. Okay, it's like saying there's the richest person in the world or there's the richest person in Calgary, right? These are like, this would be the richest person in Calgary. It's locally, it's the highest point. So these guys are all local max, and these ones are local mins. Okay, so that's just some vocabulary. Okay, so we learned yesterday, actually we just did this a few minutes ago and earlier in the course, that max-mins can occur where the first derivative is 0, right? And that's because that's where the function can change from increasing to decreasing. When a function changes from increasing to decreasing, you're going to get a max point. Or when a function changes from decreasing to increasing, you're going to get a min point. Okay? But on a closed interval, which is what I just drew up there, closed interval means it starts here and it ends here. It's not like it starts here and it goes to infinity, or it starts here and it goes to negative infinity, or it starts at negative infinity and it goes to positive infinity. Okay, that would be an open interval. If it's a closed interval, okay, meaning it goes between two finite values of x, then they could occur either when the derivative is 0, or, as we just saw above, they can also occur at the endpoints. Okay? So, for example, find the absolute max-min values for g of t equals 2t cubed plus 3t squared minus 4t on, plus minus 12t plus 4 on 4, 2. That means we're looking on this interval between x equals 4, negative 4 rather, and x equals 2. Okay? So how do we do this? Well, we've got to figure out where is the derivative equal to 0 in this interval and look at the values of the function on those points, because those could be potential max-mins. And we've also got to look at the values of the function at the endpoints, because those could also be max-mins. Okay, so that's what we're going to do. Okay, so we've got to figure out look at the values of g of t when g prime of t equals 0, and look at g of t at the endpoints. That's what we're going to do. And then basically we're going to see, okay, here are the values of the function. Which one's the highest, which one's the lowest? And that'll tell us the absolute max and the absolute min on that interval. Okay? All right, so first we got to find the derivative. So g prime of t, this we can use the power rule for, is going to be 6t squared plus 6t, minus 12. Okay, so we can take a GCF out here of 6, which is nice. T squared plus t minus 2. And then this guy's factorable, which is also nice. Okay, because we're looking for two things that multiply to negative 2 and add to 1. So t plus 2 and t minus 1. Okay, so values of the derivative, that would be, this is g prime. No, there's nothing wrong there. But to solve this, we'd have to actually set this equal to 0, right? That's the step that I missed. which means that t equals -2 and 1. Okay, so what do we need to look at? What do we need to test? Well, we've got to test those two values, g of -2, g of 1, and then the two endpoints. Okay, g of -4 and g of 2. And we're basically going to compare. Once we figure out the value of the function at those specific x values, we can say this one's the highest, this one's the lowest. And that's all we need to do. Now, one thing I should mention is that if you happen to get a value of t where the derivative is 0, that's not within the interval that you're looking at, then you don't want to test that, right? So for example, if one of these t values was 10, that's not in the interval that we're examining right now. We're only examining between, I think it was -4 and 2, right? We're not interested in that. So ignore those ones. But the two values of the derivative that were of t rather, where the derivative was 0, is within this interval. So we want to make sure that we figure out what those are. Okay, so let's see. G of t, I don't have a lot of room here, but it's going to be 2 times -2 cubed plus 3 times -2 squared minus 12 times -2 plus 4. Whatever that is. You guys have calculators in front of you. Okay, g of 1, that one's easier. 2 times 1 cubed plus 2 times 1 squared minus 12 times 1 plus 4. I can do that one. I'll do that one. You guys do the rest. Yes? 3. Thank you, thank you, thank you. Once McKenna fixes it for me, then I'll do it. Okay, so 2 plus 3 is 5. Minus 12 is -7. Plus 4. This one's -3. I got that one. There we go. Okay. This one is 2 times -4 cubed plus 3 times -4 squared minus 12 times -4 plus 4. And this one is 2 times 2 squared, cubed rather, plus 3 times 2 squared minus 12 times 2 plus 4. Okay, so we still need g of -2, g of -4, and g of 2. All right, you guys are all fast typers, aren't you? Probably faster than I am with the texting these days. Okay, I got 24 for this one. But I make mistakes, as you guys know, so someone should double check this. I got -28. Did someone else get -28 there? I feel like that's wrong. Okay, someone check this one. -28, is that right? Someone check g of -4 for me. I'm not feeling confident on that one. This one I got 8. but I need confirmation. Which one? It is negative 28? Sweet. Okay, okay. Whew. All right. I still have some on my game. Okay, and the rest of them? They're good? Oh, wow. All right, sweet. Okay, so what does this mean? What's the absolute max on that interval? Yes, the absolute max is 24 when t equals negative 2, and the absolute min equals negative 28 when t equals negative 4. There we go. That would be the answer. Make sense? Yeah. Negative 24? It is positive. Yeah. Is that what you got? Negative? Yeah. Plus 12, plus 24. Okay. Whew. All right, cool. That's all good. Okay. All right. All right, guys, this is our last one. Find the absolute max min values for f of x equals 3x times x plus 4 to the 3 over 2 on the interval negative 5, negative 1. Okay, so we got to do the same thing. We've got to basically find out where in this interval is the derivative 0. Okay, figure out the value of the function at those points, and then also figure out the value of the function at the end points. Okay, so that is what we're going to do. Okay, so f prime of x. This is a product rule. Okay, so what's that? Yes, well, it is a chain rule because this is, maybe we should do this off to the side. U equals 3x, so u prime is 3. V is x plus 4 to the 3 over 2. It is a chain rule. However, the derivative of x plus 4 is just 1. Right? Because the derivative of x is 1, the derivative of 4 is 0. So it is a chain rule because inside here is another function, but its derivative is 1. Exactly, yeah. So it's not going to make really a difference. But we should write times 1 there to be thorough. Okay? All right, so f prime of x equals u prime v, 3 times x plus 4 to the 3 over 2 plus uv prime, 3x times 3 over 2 times x plus 4 to the 1/2. Okay? And let's see. We're going to have 3 times x plus 4 to the 3 over 2 plus, what is this, 9 over 2x times x plus 4 to the 1/2. Okay, so I think what I'm going to try and do here is factor out and x plus 4 to the 1/2, because that's common to both, okay? And actually, I can factor out a 3 as well. Times, this is going to be just x plus 4. Because if I take a half of that away, I'm just left with x plus 4 to the 1. Okay. And then here, I'm going to be left with, if I take out 3, plus 3 over 2x. Does that make sense? All right. Okay, so let's just, maybe I'll sort of tidy this up a bit and also set it to 0 at the same time. So this is 3 times the square root of x plus 4 times, let's see, 3 over 2 plus 4 plus 1 is 5 over 2 x plus 4. Because I've got 3 over 2x plus another x. Yeah. Okay, so what would make this 0? Well, x could be negative 4, right? Because then negative 4 plus 4 is 0. The square root of 0 is 0. And then this piece is 0, right? So from here, we get x equals negative 4. From here, let's see, we're going to get 5 over 2x plus 4 equals 0. So 5 over 2x equals negative 4, which means (5x) equals negative 8, which means x equals negative 8 over 5. And you know what? I'm going to write that as negative 1.6, because I don't really feel like putting in fractions. That's going to be a bit of a pain. And it's a terminating decimal, so I don't have to worry about, like, I'm not going to be rounding if I convert it to decimal. So I'm very happy to do that. Okay? So to find absolute max and absolute min on this interval, I need to look at a bunch of different values of f of x. I need to look at f of negative 4, f of negative 1.6, and then the endpoints, f of negative 5 and f of negative 1. Okay, now the original function was f of x equals 3x times x plus 4 to the 3 over 2. Maybe I'll write it down here because I'm running out of space there. Now, x plus 4 to the 3 over 2 is the square root of x plus 4 cubed. And it might be more helpful to look at it that way when we substitute in. Okay? So f of negative 4 is 3 times negative 4 times the square root of negative 4 plus 4 cubed. What's that going to be? 0, yeah, because this piece is 0. So this is 0. Okay, now you're going to have to get your calculators out for this piece. 3 times -5 times the square root of -1.6 plus 4 cubed. Oh yeah, what did I have negative? Oh, I was looking down there. Thank you. Yeah. I'm not a good multitasker. Okay, so what is that? Times. I'm getting 17.85, negative 17. That's what I got. Is that what you guys got? Crossing my fingers. Yeah? Can I have a confirmation? Yes. Sweet. Okay. Now this guy, what's going to happen here? 3 times -5 times the square root of -5 plus 4 cubed. Doesn't exist. Yeah. Doesn't exist. This is outside of the domain of the function. Okay, so the interval that we're actually examining doesn't include the entire domain of the function. The domain of the function only starts at x equals -4. Because if we take anything lower than x equals -4, we're going to be taking the square root of a negative number. Okay, so x must be greater than or equal to -4. That's the domain of our function. Okay, and then finally, this is 3 times -1 times the square root of -1 plus 4 cubed. And that is I'm getting that. Yes? Whew. Okay, there we go. So for this interval, our absolute max equals 0 at x equals -4. And our absolute min equals that, -17.85 at x equals -1.6. That's all I have for you today. This is a rather tedious unit. We've got to go through a lot of analysis, right? And this is kind of just the start because we haven't actually brought in the second derivative yet. So we're going to start to do that next week. Okay?